Okay, so let's start the class. So turn on the video. And today we have the 5 presentations. So the Jordan, Grant, and Parsa, and Andrea, and Lex. And I ask you to comment on each presentation in Canvas. So you can see in the quiz section of Canvas. So make specific comments. So not just like great presentation, just a specific comment on this regression model is good or something like that. And at the end of the class, at the end of the course, I will ask you to vote for the best 3 presentations. So just keep memo so that you can remember which presentations are good. Okay, and the presentation is 12 minutes. So after 12 minutes, I say it's 12 minutes. So you can wrap up presentation in 1 minute. Of course, the shorter presentation is fine. And I will, you can ask question to presenter, but maybe just one question because of the time limit. Okay, so now we can start. So Jordan, can you go first? You can share the screen.
Okay,
Hi.
yeah, I can go first.
Yep.
Let me see here. Shit. Okay, and then
Yeah, you can start. Yep.
okay. So hi, I'm Jordan, and today I'm going to be talking about demographic characteristics of enrollment at a Michigan community college. So I work at Schoolcraft College, which is a community college in Livonia. Um, for this project, I asked our data team if I could conduct an analysis on an enrollment data set. So they provided me with 8 semesters worth of data, anonymized record level data that describes enrollment in the college's different degree programs with demographic attributes. So my objectives um, that I accomplished are assembling descriptive statistics to examine the demographic differences in enrollment, and then using Pearson's chi-square test to examine if enrollment in different career pathways and programs uh, are independent of demographic factors, or if they follow similar distributions between semesters. Um, and then as I was exploring the data set, I found that more the more I explored, the more questions I had. So I wanted to have just a little fun with it too. So the samples, the data itself is 44,933 observations of 20,133 students, and it covers 8 semesters from the summer of 2021 to the spring of 2023. And it represents the complete population of credit students at Schoolcraft for those semesters. The variables of interest, career pathways, which are sort of the bins that different degree programs get put into for organizational purposes. So I was looking largely at uh, uh, the career pathways since there are fewer of them, so that's easier to analyze. And then demographic variables that I looked at were gender, race and ethnicity, age category, uh, credit load, full-time versus part-time, veteran status, Pell Grant status, distance education, and city. And you on the right-hand side, you can see a list of the different career pathways that the college has organized their programs into. So for description, I assembled tables, which are pretty much just in my code, because I thought bar charts would be easier to give everyone a brief glance at the distribution of enrollment. And then I also assembled a map which counts the frequency of residents of different where different students reside. And for analytics, I used Pearson's chi-square test with the null hypothesis that either factors are independent of each other or that the distributions are not different. And I used an alpha of 0.05. So I decided to start by just summarizing the entire population. Because an individual student might be enrolled over multiple semesters, they could have multiple variables if they switched degree programs or moved into a different age category. So for the overall statistic, I took the last record that the student had in the data set, and this is an arbitrary choice that makes analysis convenient for me. I don't know how that might affect the analysis. So I assembled some bar graphs to show proportion of enrollment. So on the left, in the different career pathways, as you can see, about 40% of students at Schoolcraft are not enrolled in any degree pathway. A lot of those are guest students from other schools taking a single class. On the right, you can see age. Maybe unsurprisingly, the largest demographic is the 18 to 24 age category. By gender, about 60% of students during this time were female, about 40% were male. And by race and ethnicity, about 60% were white, about 20% were black, and the rest of the race and ethnicity categories comprised less than 10% each. And this is a map that I assembled that shows the 20 cities most frequently listed as the city of residence. So Schoolcraft sits between Northville and Livonia, and as you can see, the biggest pool of students is drawn from Livonia, Canton, Plymouth, Northville, Westland, which makes sense because they're all very close. For the second part of my analysis, I wanted to compare results compare enrollment between two semesters. So I chose fall of 2021 to fall of 22. And the things that I thought were interesting were that in these two bar graphs, one describing each semester, these are counts of students enrolled in the different career pathways, grouped by gender. So you can see that some of the career pathways are wildly different enrollments by gender. But if you look between the two semesters, the distribution looks the same. So first I wanted to ask, is the enrollment in programs in different career pathways independent of demographic factors? So I ran Pearson's chi-square test on each of the factors in these two. And as you can see from the very low P's, distribution is not independent of any demographic factor in these semesters. And the second question I wanted to ask is, does demographic distribution of different pathways differ between corresponding semesters of different years? So example, from fall to fall, to summer, winter to winter. And as you can see here, from these p-values, which are all above 0.05, the distribution between corresponding semesters in these 2 years are not significantly different. And then the final question I wanted to highlight that I had is taking enrollment in one single career pathway, and that's the STEM pathway. So like with the summary data, I subset everyone who was enrolled in a STEM program for at least one semester and I took the record for the last semester that they were enrolled in a STEM program. Same caveats as with the general population. A couple of things that I noticed on the left is enrollment for STEM programs by gender, and the general is on the right. So as you can see, the distribution looks very different. So I wanted to see if that was different. And just sort of intuitively, the two distributions for race look very similar to me. So I was curious about if they were distributed similarly by race. So I ran Pearson's chi-square test using the null hypothesis that the distributions are not different. And except for the Pell Grant variable, you can see that the demographic distribution of STEM students was significantly different from the distribution of the general population described in the data set. So in conclusion, I think I was really interested to see how I was really interested to explore different distributions by factor. I think there's a lot more I could do. I'd love to be able to dive more into the geographic data. It was a real bear to wrestle with, but I think that using census or distance data, I think you could assemble some really interesting factors. And I think you could explore more between more granular factors to see how they are distributed. And while these data are interesting, I think it would be unwise to draw too many inferences from them because enrollment in a program, none of these demographic factors, explain why someone would choose to go into a certain program. There's no logical causal pathway there. So instead, they should help us in formulating questions for further study. So why are people with different demographic characteristics drawn to one program or another? Or if we wanted to increase an underrepresented population's enrollment in a program, how would we make it more attractive or better recruit students? I think that there are probably other qualitative studies that you could start to ask students those questions. So that would probably be my next step, is to take those questions and do qualitative or quantitative studies based on those. And yeah, thank you. That's all I have.
Okay, thank you. So does anyone have a question to Jordan? Jordan? No questions? Yeah, I think this is interesting study. So often the college enrollment statistics only see the marginal distributions and they don't see the relationship between two variables. Yeah, for example, we have more female students, but the one driving factor is that the male African American male has very low enrollment rate. So that kind of finding cannot be found without seeing this kind of contingency tables. Yeah. Okay, that's great. Oh, do you have a question? Yeah.
Yeah. Could you go back like a couple of slides?
Oh, sure.
Where there was the bar chart with the different groups or the different fields.
Yes. Was it this one?
Yeah. What do each one of these mean?
Okay, so the x axis, each of these, just to make the chart readable, I had to abbreviate the different career pathways. But so these are the different career pathways from the right side. here. So those are groups that like the different programs are grouped into. And there are just a lot of programs, so it was more convenient. Basically, it was a measure, a means of convenience to be able to present the data legibly.
Thank you.
Okay, so next presentation, we just okay. Okay, so next one, maybe Grant. Can you share the screen? Okay, you can start. I cannot hear you.
Sorry about that. All right. So for my presentation, I'll be talking about tracking race windows for CT scans or computed tomography. Oh, let's see. So a little background, as you know from the news and whatnot, that race windows increases the risk of cancers for everyone. And as a conservative assumption, we typically go by this linear no threshold model where any type of radiation dose that you receive increases your cancer rate. Although statistically, it hasn't been found that it actually increases cancer towards these low dose range. But as a conservative assumption, we like to use this model. And so because we're using this model, it's very beneficial to patients to practice what we call ALARA, a low as reasonably achievable. We don't want to overdose the patient more than necessary. And so now, whenever you go to hospital, docs and medical professionals like to order CT right away because it provides a great benefit. But at the same time, we want to limit the amount of dose if we can and if we don't need to. So now hospitals nowadays have to track CT ration dose as a part of requirement by the federal regulation because now CT really accounts for about a quarter of the ration dose to the public, and we want to limit it as much as we can. And we want to track if it's, if we're doing the right thing for the patient and not overdosing them. And this really leads to my motivation of the project, but also motivation for taking this course is that as part of my work, we are tracking ration dose, but we have a limit that we kind of flag patient scans in case it, you know, we get a really high dose and we want to investigate what went wrong or what could we have done better and so forth. But that limit is kind of universal across patients. I want to look at the data and see, are we prescribing the correct amount of dose? For example, should we be using the same amount of ration dose to toddler as adult or a 150-pound patient versus a 300-pound patient? So my objective is to establish dose benchmarks based on the available patient descriptors that when a patient comes in, can we sort of identify outlier, dose outlier based on if by their age or by their weight and so forth. And I want to find the, if we can model it using the data that we get from the CT scanners. Then also calculate the confidence and prediction intervals for this model in order to identify these outliers based on such predictors. So I kind of just walked over to the hospital that I lived right next to, and I requested the CT dose data from the last quarter of this year and anonymized it so that we're not breaking any HIPAA regulations. And we have these data here. The first variable is what we call CT dose index. It's a surrogate for ration dose from the scanner. And this is the Y variable that we're trying to model. Using these available patient demographics. These are demographics that we have available and what I'm mostly interested in. For example, the patient type. Are they an inpatient, outpatient, or emergency patient? Also their age and their weight. Additionally, we have CT scan parameters that we get from the scanner itself in order to improve our model and see if it's helpful in our analysis. And the total amount of cases that we got from quarter 3 was about little over 3,000 data points. So taking a look at the data here, here's the dose versus age and weight. And what we're seeing with the dose versus age is that there's primarily most data points around the 60 to 80 or 60 to 90-year-old range, possibly because typically they would get probably more prone to incidents or have more health issues, or they're or for lower patients, lower age patients, maybe they're more cognizant about prescribing a dose for them. Whereas the bottom graph here, we have dose versus weight, and most of the patients are within, I guess, a normal body habitus around, the 60 to 100 kilograms on patient weight. But you can tell from our data here that there's quite a bit of outliers, and it's kind of scrunched together. So for analysis, I did a log transformation to kind of spread out the data for easier analysis. Then also by patient type, on the left graph here is the original distribution for emergency, inpatient, outpatient, and there's also outliers that's involved. However, doing the same thing as the last graph, I log transformed the dose data, and we eliminated outliers, which is fortunate. So the original data was originally very right skewed, but after the transformation, it's more symmetrical. There's much more emergency cases than we have inpatient, outpatient. Over 2,000 was from the quarter as a very busy emergency department. And also the CT parameters, here's the correlation map with the dose versus the CT parameters. I'll just quickly point out some of the key features that we're seeing. For example, when it comes to dose versus the CT parameter MAS, which is the tube current, the X-ray tube current, we see that there's a linear relationship, but there's several linear relationship. So which leads me to suspect that it has to do something with the only factor variable that's we have, which is the KVP, which on the left of that this graph here is the 4 discrete points. But also we see a high correlation between scan length and exposure time, which makes sense because the longer you're scanning a patient, or the length of the patient determines the exposure time of the CT scanner. So based on the information here, I had my first question. So do we need a different model based on patient care type? So is the dose distribution between these emergency patient, inpatient, outpatient, are they similar enough for it to apply one model, or do we need multiple ones? And more specifically, we're looking at the mean of the distribution as well as the variance. So my method was to first check the normality, check the variance, and based on the results from there, I'll form either a Welch's or a Wilcoxon rank sum test in order to see how different the distribution is. So looking at the normality, as you can see from here, they all have kind of heavy tails. The emergency, the inpatient seems very similar. It's close to normal, whereas the outpatient is really far from normal. And so I pulled up the histogram of each of these, and it's very different when it comes to outpatient. On the left histogram and the middle histogram with emergency and inpatient, it's kind of normal. You can probably argue that it is, whereas the outpatient, it's completely all over the place, which leads me to suspect, they may be using a completely different protocol on that for outpatients. Then I use the Shapiro-Wilks test, kind of overkill when it comes to outpatient, but now all of them seems to be not normal. The p-value for these are all significant, where it indicates that these are not normal distributions. Next, checking the variance for all of these. When it comes to emergency patients compared to inpatient, outpatient, we have a significant p-value using the F-test, where it says the variance is very different when it comes to emergency versus inpatient and outpatient. Whereas the inpatient versus outpatient, we have a p-value of 0.5, which is not significant at all. So it's not rejected. However, based on the last slide, we can tell it's a totally different distribution. So based on this result, I used the Wilcoxon ranked sum test for all of the clinical services because of they're not normal, but also the variance is different. So based on the Wilcoxon test, we rejected all the p-values were significant, and we rejected all of the null hypothesis, meaning that the distributions are different based on patient care type. So that leads me to the second part where I have to model each of these based on a clinical service. So part two is how can we model the dose and identify outliers? So what are the significant predictors? What are the best combination predictors for our model? And what kind of boundaries can we use to alert us of a quote high dose based on these predictors? And the method that was used was a model search by AIC to determine what, using multiple linear regression to determine what predictors is used to determine the dose to the patient. Also, I checked the model diagnostic using residual plots and also calculated prediction intervals. So this is a busy slide. However, it just kind of shows you the last step of the AIC model search and what the AIC had determined as our best model. And I'll just point out a couple points here is that the greatest amount of variation was explained by the CT parameters KVP MAS, where it's a significant drop in AIC for all three of these patient services, whereas the other ones such as weight, age, scanning length, and exposure time made the model better for emergency, but not significant as MAS or KVP. And also, very unfortunate for a result that I was looking for is that the outpatient, for outpatients, there's not a single patient demographic as the best model. So the age, the weight is not significant at all when it comes to outpatient. Whereas inpatient, the weight and age seems to be a good predictor. And inpatient, the weight seemed to be a good predictor. So checking the residual plots for emergency patients, broken down by the factor variable KVP. For the first two at 80 KVP and 100 KVP, the visual versus fitted plots seems pretty good. Whereas the last two at 120, 140, it seems to be slightly increasing for both of these, but also quite a bit of outliers towards the bottom. So it leads me to believe that the relationship may not be linear. So I'm not too confident in the model that is being used for emergency patients. Whereas for inpatients, it seems much better, although it seems kind of all over the place for 140 KVP because of the lack of data points. But it seems kind of random, and I don't really see much patterns involved. And lastly, for outpatients, there's only one KVP factor for this one, and it seems pretty random as well. So it seems like most models seems to satisfy the IID-ness, except for the emergency patients at 120 and 140 KVP. And so lastly, I calculated the prediction interval using the significant predictors in patient demographics. On the top left is the inpatient one, which seems pretty okay. It seems like the outlier does have quite a significant contribution into this model, but we can possibly use the prediction interval here to kind of identify certain cases that's above the prediction interval as possibly overdosing or just a trigger for us to investigate what's going on. But also things that are below here, maybe we're not prescribing enough dose and the image quality is bad. So these are all kind of data points that we can possibly look at going forward. Whereas emergency patient, when it comes to dose and weight, There seems to be two distributions going on here. I'm not too sure what's going on. So that's a kind of headache. That's something I need to work on and investigate. But it seems pretty. I wouldn't say confident. I'm not that confident in this prediction interval. Whereas the patient age versus dose, I don't think that's very helpful because although it is correlated and age seems pretty good, it doesn't really help if a smaller patient or a younger patient versus a higher patient.
All right,
threshold.
already 14 minutes. Wrap up.
Oh, sorry. Okay, in conclusion, it seems like the dose distribution for each patient service type was significantly different. So analysis should be performed separately. And lastly, the patient weight appears to be a good descriptor to track ratio dose for inpatient only. And because the linear regression was possible, and the predictive interval may be useful for identifying outliers. Okay, thank you.
Thank you, Grant. So does anyone have a question?
What's KVP and MAS?
There are CT parameters. I didn't want it to go too in depth into it, but KVP is basically the voltage that's in the X-ray tube, whereas the MAS is the current in the X-ray tube.
Thank you.
Yeah, I think it sounds that the data have some indication of clusters. For example, the scatter plot for MAS versus CTDI. We have the 4 different trend lines, and also maybe there's some graphs. Maybe for emergency patient, the 120, 140 kVp, it may have 2 clusters. So if you introduce some indicator variable to distinguish clusters, if any, the cluster variable, then it may improve the model fit. Yeah, but it's very detailed analysis, and it's very nice, and the data set is also original, so it's very good. Okay, so next one, the parser.
Oh, I'm nervous.
Okay.
Oops. You see that?
Yes.
All right. Well, we're going to be going from CT scans to avocados. So let's dive right in. I have a lot of slides, so we'll have to go fast. Avocados, they're a delicious fruit, and recently they're not, well, for a couple of decades there's been a craze going on regarding avocados. Some people have been calling them superfoods, and there's a lot of interesting history behind avocados. I won't go into depth about that, but basically we're going to be analyzing how avocado consumption and production has evolved over time. And what we're going to be using for our data set is going to be data from the Haas avocado board. They have volume data, and they have volume projections and data from 2021 to 2024, with the end of 2023 and 2024 being predictions, and the rest being measured data points. These contain basically like the amount of pounds of avocados that major countries are producing, plus California for some reason. And they also contain categorical data. Basically, this contains things like the average selling price of avocados by type, like whether it's organic or not, and by size. And this is from 2020 to 2023. It also contains like how many units are sold and the total revenue of various countries and regions. Our objective here is going to be to figure out where avocados come from. We'll be using a time series plot to look into that. We also want to see how does the type of avocado impact sales. That is, if you have an organic avocado and you have a conventional one, How different are they, or are they different to begin with? And we'll be looking to a correlation matrix of the units sold by type. That is, like, if you have a small conventional avocado, how does that correlate with, you know, a large organic one? Then we'll be going into how well avocado prices can be predicted with past data. And we'll be looking into how the general supply and revenue from avocados have evolved over time. And we'll be using some linear regression models for that. So the first question is, where do avocados come from? As you see here this is a time series plot of the volume of avocados produced in millions of pounds from the year 2021 to 2024, with late 2023 and 2024 being a prediction. So there's a few points we can notice from here. It's that most of the avocados are being produced in Mexico. And California and Peru make up the most of the remaining proportion of avocados. Chile, Colombia, and the Dominican Republic, they're essentially negligible in the grand scheme of things, but they do contribute some avocados to the global market. Also notice how there's a seasonality to Mexico's production, and when Mexico's production dips, you have a rise in California's and Peru's production, and what you end up with is the total volume. Sort of, it's volatile, but it doesn't dip as much as something like Mexico's production. So yeah. Now we're going to go on to how the type of avocado impacts sales. On the left, we have a box plot of the average selling price of conventional avocados by unit. And we have conventional organic on the left and to the right. The first thing to notice about this is that the median of the conventional avocados is smaller than that of organic. But the organic one has more outliers, and it has a slightly larger spread than conventional avocados. On the right, we have a table containing the mean and standard deviation and variance of the price, or the average selling price, of conventional and organic avocados. The mean for conventional is about 1.1, and I can't really see the mean on my screen because the camera's covering it, but I think it was 1.6. So on the bottom right, I use Welch's t-test to compare whether the means are equal to each other, and as you might guess, they're not. And with a p-value of something really low, I can't really see it because the camera's in the way. We can reject the null hypothesis that the means are equal to each other. And the confidence interval of their difference is between negative 0.5 to negative 0.53. So clearly not zero. Now, was the t-test justified? Well, according to their QQ plots, they seem quite straight. So it seems to be justifiable that like it's likely that that distributions are normal. So t-test was likely justified. Now here we have a correlation matrix for the units sold of each type of avocado. And the most striking thing about this correlation plot is that there's a lot of there's low correlation between organic 4770 avocados and everything else. So I first want to explain what the numbers mean. 4046 is a small to medium avocado. 4225 is a large avocado, and 4770 is an extra large avocado. Everything seems to have high correlation with each other, but the small correlation on for the organic 4770 avocados, I looked into the numbers, and it seems like a lot of the values for organic 4770 has unnaturally low numbers. Like it goes from 10,000 or like 100,000 down to data points that have like 0 or like 10 or 5, whereas all the other avocados, they're consistently around the 10,000 to 100,000 range. So it's likely possibly a data collection error, or something like that. But but it's likely that they're probably all highly correlated with each other. It's just the data might have been collected poorly. Now, I wanted to see how well avocado prices could be predicted given previous year's data. So I wanted to see how the change in price is influenced by the prior year units and the prior year sales. Doing a linear regression model on these two predictors gives us an estimate for the intercept being around 5 times 10 to the power of 4, and for prior year units 4.708 times 10 to the minus 1, and prior year sales is negative 4.4 times 10 to the minus 1. Now it's important to point out that since the average selling price of avocados don't vary much over time, they're between 1 to 1.3. You would expect the prior year units and the prior year sales to be closely related to each other, because the prior year sales is just the prior year units multiplied by its average selling price. That partially explains why the values for the estimate for the prior year units coefficient and the prior year sales coefficient are so close to each other. But the I can't see, the camera's in the way. Give me a second. But we do have a significant p-value for where am I? Yeah, a significant p-value for the coefficients for the prior year units and the prior year sales. Not so much for the intercept, which is peculiar because, well, I mean, it is quite peculiar, but the total model overall does have a very significant p-value. Its adjusted R-squared is close to its R-squared, which is 0.24, which is not that great at prediction, but we could do better if we had more data. But I noticed that when I was looking at the residuals, their distribution wasn't normal, so I decided to transform the variables, or more specifically the response variable, to get something that looks more normal. So I decided to take the fifth root of the change in price, and the resulting residuals of this new linear model seems to be more has a more straight and normal QQ plot, which would indicate more normality than our previous model. And with that, we got very similar. The coefficients on the top are incorrect. The ones on the bottom are correct. But we got what's strange here now is that the intercept is now significant, and now the prior year units is no longer significant, and the significance for the prior year sales is slightly less significant, but still considerably has considerable significance. The R-squared has improved to 0.4, and the adjusted R-squared is close to the R-squared value, and the p-value is very significant. So yeah. Next, I wanted to know how the general supply and revenue from avocados has evolved over time. This is the number of avocados sold in the entirety of the US from 2020 to 2023. This is a simple linear regression model where time is going to be the response variable, the predictor, and the units is going to be the response variable. And the first thing to notice here is that there seems to be a slight downward trend. Another thing to point out is there seems to be some periodicity to the number of units sold. And I'm gonna get into that later, but right now, this model, it clearly has a negative value for its for the slope. And it's important to point out that this time variable is the number of days from 1970, or January 1st of 1970. So the intercept will look very large in comparison to the values here, because here we have 2 times 10 to the 8 for 2020 for the number of units sold, whereas the intercept here is 5 times 10 to the 8. And so it's just you'd have to take that into account that it's from 1970. So that's why the intercept is so much larger compared to what the intercept looks like on this graph. But
12 minutes.
Okay, but both of those are significant, and the whole model has quite a high significance, but only r squared of 0.2. The QQ plot seems, the residuals seem normal for this one, but I decided to take advantage of the periodicity and add a sine curve to this. I wanted to take a phase shift into account, so I added both a sine and a cosine curve. And I'm dividing 2 pi by 31 million because that's the number of seconds in a year. So that gets us a period of 1 year. And this model has a better r squared value of 0.45, and most of the coefficients are significant. The time is still negative, or the coefficient in front of time is still negative. So basically, avocado sales in the U.S. have been going down slightly over the past couple of years. And basically the amplitude of the sine wave is has an amplitude of 10 times 8 times 10 to the 6th. So there's significant fluctuations from month to month, or throughout the year. I also want to do the same for revenue. Since I'm running out of time, I'm just going to speed through this. Okay, yeah. Yeah, okay. Thank you for following me on this journey. Do you guys have any questions?
Any questions? Yeah, I have never seen any person who are this serious about avocado. And yeah, so the one thing I have to mention is that for time, the regression about the time trend. So the maybe you can show, yeah, that one. Yep. So this class doesn't deal with this class doesn't discuss how to deal with the time series, but for this one, the residuals are, they're obviously highly correlated for adjacent observations. So actually we cannot really rely on the p-values. The estimating trend is fine, but to see the significance of trend, we need somewhat more advanced methods. But yeah, it's very interesting to see how avocado market works. And
I have a question.
Go ahead.
Do you have any ideas about why avocado consumption is decreasing? Seems to be decreasing.
I'm not really sure. Maybe one guess could be like the superfood trend is it's like a while back, and maybe it's been dying down over the past couple of years. So it's possible that might be a reason why the consumption has been going down slightly. But I mean, there's still people consuming quite a lot of avocados, but it's been going down slightly. That's my guess. Any more questions?
That's great. Okay, maybe go to the next presentation. Andrea?
Yep. Okay, let me start sharing my screen.
Sure.
Okay. Oh,
it's do you have the green button maybe at the bottom of the window?
It's telling
green
me
up arrow button.
It's just that it's telling me to give permission for my unlock it in my computer.
Oh, I see. So maybe I have to do something. Just a moment.
It says leave meeting in order to open system preferences and grant access to application.
Maybe I make you co-host
Oh, okay.
And possibly
And then
you can try that again. Yeah.
let's see. This one. Can you see
Yeah.
my screen?
Yes.
Okay, perfect. Okay, so today I will be discussing sentiments versus sense, an analysis that's going to be happening on media sentiments and its effect on stock returns. Oh, okay, so I will be focusing again how sentiments that are being expressed in titles specifically of financial news sources may correlate to the growth or decline of stock prices. And for this project, I decided to focus on the tech industry, specifically Apple, Google, Microsoft, and some more sampling decisions. I chose to do an analysis over the past 2 years. So from January 2021 to January 2023, hoping to get more recent and more applicable realistic data. And the financial news sources that I will be drawing my information from is from the Wall Street Journal, Barron's, and Market Watch. So to break down the data, there were 2 big steps that I needed to take in my data extraction. There's the sentiment value or the sentiment data, and then there's the stock data. A bit about the stock data, I was able to get it from Yahoo Finance, and it was just like a simple historical stock data that I was able to extract and modify. But for the sentiment data took 2 different phases. The first phase was the actual extraction. I had to create a Python script in order to scrape articles and maintain those parameters that we have established earlier. So again, the date frame, I needed to make sure that the articles were published within that time frame. And I also needed to make sure that the search was Microsoft or Apple or Google. I then used that to parse through it and then extract the content that I needed. So the title, the publication date, in order to correlate it over to the stock data, and the article link for future use if necessary. And then I converted it to a CSV file. Next, I needed to actually extrapolate the sentiment value. So I will be touching a little bit more on the next slide, what the sentiment value is and why I used a sentiment value. But essentially, we have NLPs, which are natural language processors. And in that library, they have sentiment values available, which allows us to create more objective decisions on the sentiments of a certain phrase, context, or some text. So the sentiment value is actually made up of 4 components: the positive, the negative, the neutral, and the compound. The positive is a value that is extrapolated from words that are more optimistic or favorable, while the negative is more pessimistic, unfavorable, the opposite to what you would assume positive is. And then neutral are more impartial words. But for the purpose of this research, I focused more on the compound value, because the compound value takes into account all 3 of those values and sums it up into one central value. Another notable thing to mention is that each of these values is, it ranges between plus or minus 1. So if it's 1, it means that it's extremely exists and it's very prevalent in the text, and the negative 1, it's less present. So let's understand the sources themselves. So I used Barron's, Market Watch, and the Wall Street Journal, and I decided to put the different stock values into a scatter plot that summed them into their own categories in order to see if the source itself had a more objective or a more biased perspective. So from this data, you can see that the Barron's, for instance, has the strongest maximum. So it has the highest maximum. So it might have had an outlier, a very strongly positive article, while Market Watch has a very strong minimum. I also want to take a look at the quartiles. Although I believe it was, sorry, I'm trying to, although Barron's does have like a very strong positive value or maximum, the Market Watch quartile, third quartile, does show to be higher than the third quartile of the Barron's one, which shows that it does generally it's more positive or inclined to be positive than Barron's is, although Barron's has the most positive article in the data set. And then another notable piece is if we take a look at Wall Street Journal, you can tell that it tends to be a lot more flatter, the data, and it's more centralized, which shows a more objective perspective. You can see this or quantify it through the frequency of 0, how much it appears through the data set. And again, at Wall Street Journal, they have nearly 50% of the data is zeros or very neutral. So next, to better understand the variables for this analysis, because I want to see how the sentiment value has, whether it's correlating to the logarithmic return rate, the independent variable here is the sentiment value, while the dependent variable is the logarithmic return rate. And for the logarithmic return rate, I chose to leave a 3-day lag, which essentially means that I'm accounting for leeway, whether that is like human error or if like a contract is announced in the media, then it might take 3 or 4 days to implement. So that 3-day range seems like a good half week to consider updates into the stock market that may result from news that appears in the media. So next, I went ahead and created a scatter plot that focused on the stocks themselves. So we have Microsoft, Google, and Apple. And then the line in the middle is the logarithmic return. But to better see this, and again, like I mentioned previously, the sentimental value ranges from -1 and +1. So I went ahead and scaled it by 1/10, so we can see a better link to the actual logarithmic return. And so by taking a look here, you can see naturally there were a lot more articles published by Apple or about Apple. And then another interesting thing to note is that a lot of these dots don't seem to align with the spikes. So the spikes seem to, like the Google, if you take a look at Google, early January, not a ton of articles are very positive when that large spike occurred. So that's just a little brief descriptor that I noticed. But I ended up using a polynomial regression to try and see whether there is a good correlation between these two variables. So here are all the 9 different polynomial regressions which arised. Unfortunately, a lot of them were, they became linear regressions when I had coded, I did a correlation between the 2 variables, and it showed that there wasn't a very strong correlation between them. And then I hoped that a polynomial regression could hopefully incline stronger data. But again, to summarize these 9 polynomial regressions, the p-values for all of them were much larger than the 0.05 threshold. And I believe the smallest one was 0.96, which showed that the actual, it didn't have any statistical significance. Also, the adjusted R squared value, it was near 0, which implies that, again, the regression is not a good fit for the model. And that would imply that the sentimental value of the financial news source wasn't a good predictor of the stock's return rate. I then wanted to take a second look at the data and hopefully by quantifying more data, and condensing them into 3 different polynomial regressions, I was hoping to find a pattern. So I went ahead and condensed Barron's, Market Watch, and the Wall Street Journal all into 3 different subsets, and then analyzing the data that arose from that. And again, I found very high p-values and not very strong correlations. But again, a very interesting thing that I saw a pattern throughout these 3 graphs was the 0 value, which could be disturbing the data. And so my next step was to consider removing the 0 value, simply because the 0 value implied neutral or objective news reports. So I wanted to analyze more so the whether something is positive or negative, and see if there is, again, some kind of regression. And I kind of stumbled upon the same predicament where the p-value was very large, and so there was no great significance statistically in the data set. But I wouldn't necessarily stop here, just because some additional considerations. I do believe that the title could have been a very big limitation, because I am using a sentimental value, and the way that NLPs work, they extract words that are redundant or unnecessary. So words such as of, to, the, those are extracted before the analysis actually happens. And then it looks for more influential sentimental words in order to create an analysis. So having a very short sample, or having a short text, can influence the actual sentimental value. Another thing that I did take a small look into was Wall Street Journal and Barron's both provided a title alongside the article description, which I was able to extrapolate. And I wanted to try and conduct a little bit of an analysis on that one. But unfortunately, Market Watch did not have or didn't provide a summary description to the article. And due to copyright issues, I wasn't able to extrapolate thousands of articles and the content from those articles specifically.
12 minutes.
Some more considerations that I think would be interesting to look into in the future is the lagged logarithmic return, and whether or not extending it another week to see the delays that a human's response might be to the actual publications. And the density of articles, the frequency when they're published, might also lead to like bandwagon effect. So human interest on whether or not, if they see a lot of Apple news reports, how that could affect the stock. And I also think that time could also influence the patterns of the media's titles. So again, maybe in 2008, during the recession, titles could have been either more accurate or less accurate, which I think would be an interesting thing to take a look at. But at the end of the day, can opinionated titles in financial news guide our stock intuition? No, not by themselves. They can't really lead to a good conclusion. Any questions?
I have a question. So when you did like the second look of your data, like you combined the data, how did you combine it? Or
Right, so let me see. Is it this one, or because I combined it? Essentially what I did, because there are 3 different sources, so I received, let's say Market Watch published a lot of articles in August on Microsoft, while Barron's published a lot in September. Then by combining the 2 and averaging the data at that time, it's more so taking a more like a larger perspective from the news source themselves. And I was hoping by creating a more continuous data set, I could find some kind of regression or pattern between the two connections.
Okay, thank you.
I have a question.
Mhm.
Could you tell us how long it took you to analyze all these and collect all these data points?
Yes, so the Python script that I actually wrote, I had to run it a couple of times and ran into a couple problems with the API kind of fetching information and being limited. But essentially it ran for upwards of 2 hours to extract one set of data. But yeah, it was a
Do you have
learning process.
Do you have any experience before to collect this sentiment data?
So this was actually my first time digging into both web scraping and sentiment values. But the sentimental value wasn't very difficult to implement because there is the NLTK library that already exists out there. And it's really easy to implement once you like install all the Python, everything that you need. And essentially you just feed text to it. So you can, initially when I started this project, my goal was to scrape the website links from all the different search pages. And that's why it took upwards of 2 hours. And then afterwards, I wanted to take those links to open them again and then extract from those links the content themselves and then store it. But with subscription-based websites, authentication keys and other like restrictions come into play. And although I have an authentication key, it was more so terms and conditions. But it was a very interesting cycle to mess with and a lot of learning.
Yeah, it's very interesting, the data collection. Yeah. Okay, thank you. Okay, so the last presentation is by Lex. Can you share the screen?
Yes, let me just find it real quick.
Maybe.
All right, can you see my screen?
Yes.
Okay. All right, so my presentation is on the Major League Baseball batting analytics. So there are like 20 different categories within batting analytics alone. So I decided to focus on 2 specific categories and the correlation between the two. So in this presentation, I'm going to talk about how I gathered my data. I'm going to visualize the categorical data, the 2 categories that I'm going to be talking about specifically. The results from running a paired t-test, comparing them against each other, overall results from my research into this topic, and then a quick conclusion. So for this data gathering, I picked 25 Major League Baseball players with the help of some friends I have who are baseball fans and websites listing top-ranked Major League Baseball players. I gathered their individual career batting statistics from the ESPN website and then compiled them into a Microsoft Excel spreadsheet. So for all 25 players, each year of their career is in the spreadsheet along with all of their stats for that year. And then I did data cleaning once it was in my Excel. So there were over 20 columns. I reduced it down to 4, specifically the player name, the years of experience they had in the major leagues, their home runs for each year, which is one of the categories that I'm going to be talking about, and then their slugging percentage for each year. So going deeper into these categories, home run is pretty well known, but it's a hit where the player can run all bases without stopping and score a run. And in their statistics, when they hit 1 home run, it's just +1. So that's a pretty simple statistic. And then slugging percentage is the total number of bases a player records per at bat, and they're not all valued equally. So I have this equation here. If they hit a single, it's just by itself. If they hit a double, it's multiplied by 2. A triple is multiplied by 3, and then a home run is multiplied by 4 because they will have hit 4 bases in. And that is all divided by the number of times they were at bat. So this slugging percentage is going to be a value between 0 and 1. So diving deeper into the data, these are the 25 players that I chose to study for this project. The part that I wanted to mention, though, is down at the bottom. I said originally I included Miguel Cabrera, Luis Gonzalez, and Ken Griffey Jr., but I ended up having to remove them from the data set just for my ease of analysis, because these three players had multiple years where they hit their maximum number of home runs. So it was difficult to compare home runs and slugging percentage, because the values of the data sets were different, because some players had multiple best years for their home runs. So I ended up removing them and replacing them with different players. On the left here is just a quick screenshot of what the ESPN website looks like. It's not showing all of the columns, but there were 20 columns of information, but it's just showing each player's season that they played, the team they played for, and then all of their batting statistics. And the website does have their batting as well as their positional statistics, but I've been just focusing on batting statistics for this project. So the data cleaning that I did, the original is on the left here, where you can see it has 20 columns of information. And in the second column, it still shows their years that they played. And then I cleaned the data, reduced it, and on the right now their years is the number of years they played in the Major League Baseball versus the actual year that they played. And then I got rid of all of the extra data except for their home runs and their slugging percentage that they hit for each year. So visualizing this data, I made a data table and a graph for both home runs and slugging percentage, analyzing each of the 25 players' best year in their career for home runs and slugging percentage. So here is the data table for each player's home run. The maximum number of home runs ranges from 15 to 73 in a single year, and the best year for home runs ranges from 3 to 15 years in the major leagues. So looking at the data table specifically, on the far left is player name. That second column is their maximum number of home runs they hit in their entire career. The next column is which year of their career they hit their maximum number, and then the corresponding slugging percentage that they had that year. And then I also displayed this in a graph just to kind of visualize it and really make it easier to see how players compare to each other. So up in the very top right, we can see this is Barry Bonds. Year 15 is his career. He was the one who hit the maximum number of home runs in this data set, which was 73. But he is kind of an outlier. Generally, the maximum number of home runs happens somewhere between year 5 and year 11, and it was generally between 20 and 50 home runs. Anything below or above that is somewhat of an outlier. And then I did the same thing for slugging percentage. So on the left is player name, and then the second column is now their slugging percentage, their best slugging percentage that they hit their entire career, which year that happened, and the corresponding home run that they had, the number of home runs they had that year. So the maximum slugging percentage ranges from 436 to 1,000, and the best years for slugging percentage ranges from 1 to 19 years in the major leagues. I just want to mention hitting 1,000 for a slugging percentage is a perfect, they hit perfect. They could not have performed any better, and that's pretty impossible to do. And this was done by Chipper Jones, and it was done in his first year in the major leagues. And this is because he only played 8 games out of the 180 games that they have in a season. So he is an outlier, and if I were to do this again, I would probably set some kind of limit on how many or what their slugging percentage has to be, or how many games they have to play, just to get some more accurate data. But again, this is the data displayed in a graph. So up in the top left, there's Chipper Jones hitting 1,000 in his first year. But more generally, on average, the maximum slugging percentage for players ranges from years 6 to 14 in the major leagues, and generally ranges from 0.5 to 0.7. So with this data that I gathered, I ran a paired t-test, which is essentially comparing the best year for home runs versus slugging percentage for each player against each other. So the null hypothesis is that there is no significant difference between the two groups, and the alternative hypothesis is that there is a significant difference between home runs versus slugging percentage. So on the right here is the raw output that I had to this, and analyzing it on the left, I chose a significance level alpha of 0.05. And the p-value that the paired t-test put out was 0.9, which is clearly greater than the alpha of 0.05. So we failed to reject the null hypothesis. And then looking at the critical value as well, this was found in a t-chart. It ended up being 3.2 about, and the t-value that was in the output from the paired t-test is 0.05. And since this t-value is less than the critical value found from the table, we again fail to reject the null hypothesis. So rejecting this means that there is not enough evidence to claim a significant difference between home runs and slugging percentage. So overall, now just looking at the results from that information, we are going to interpret the correlation between the best year for home runs and best year for slugging percentage in each player's career. So visually, 25 players, 13 of them had their best year in terms of home runs and slugging percentage in the same year. So I just circled them on the graphs here. But that is about 52% of the data set, so definitely over half. So this just by itself suggests that there is a correlation between success in home runs and success in slugging percentage in their careers. And then again, going back to the test results, rejecting the null hypothesis means there is no significant difference between home runs and slugging percentage, since the p-value is greater than alpha and the t-value is less than the critical value. So rejecting the null hypothesis means there is a strong correlation between number of home runs and slugging percentage for the players, and it is not by chance that so many players had their best year for home run and slugging percentage at the same time. And then thinking about it logistically, home run is a highly successful hit, so and it is multiplied by 4 in the calculation to calculate the slugging percentage. So the more home runs that a player hits in a year, it makes sense that their slugging percentage would be higher. So the correlation does make sense. Then these are just some descriptive statistics that don't necessarily contribute to the analysis of this data, but I wanted to throw them in there anyways. So the mean, median, and mode for both categories. So for home runs, the mean is 22. So on average, the average number of home runs hit was 22. The median, or right in the middle, was 21, and then the most common number of home runs hit was 23, which does fall between that range where on average most players seem to hit their maximum number of home runs. And then for slugging percentage, the mean was about 0.48, the median was 0.484, and the mode was 0.43. Again, falling in that range, that's where most players seem to hit their highest number of slugging percentage, was right about in that range. So something interesting that isn't necessarily related to this data, but would be something to pursue further in another project, is players who did performance enhancing drugs. In this data set, I have 6 players who are known to have done performance enhancing drugs. And then just in this little timetable here, I showed which year of their career they were known to have started taking those drugs, and it could have continued past the year that I listed. Like, for example, Barry Bonds he was using the drugs from 2001 to 2006, but I only listed that he started in 2001. And looking at these stars that I have on the timeline, these are 3 players who had their maximum number of either home runs or slugging percentage in the year that they were taking performance enhancing drugs. So one could assume that the drugs had something to do with their performance. So since sports statistics has seen such a massive growth in PED use, it would be interesting to calculate their max performance in their career, again, excluding years they were known to have been using performance enhancing drugs. So overall, what I learned from this data project and this research is that there is a strong correlation between the success in home runs and in slugging percentage for players in the major leagues. Since there are visual similarities in the data, and the paired t-test rejected the null hypothesis. And that is the end of my presentation.
Thank you. So does anyone have questions?
I have a question.
Yeah.
So for the slugging percentage, you're multiplying the if it's like a home run, you multiply it by 4.
Yeah.
Yes, correct.
So could the slugging percentage be larger than 1?
No, since you're dividing the
I think it can exceed
Okay.
1, right? In some cases.
yes.
Yeah.
It could. I
It's
guess.
rare,
But
but
I didn't see that in my data.
yeah. It's
Oh,
very
so
rare.
in the data it went up to 1.
Yes.
Do you know if there were any in park home runs included in the, or is there any distinction between hitting it out of the park or an infield or an in park home run?
There was not any distinction in the research that I did. I'm pretty sure just any hit where the player was able to run all 4 bases continuously was counted as a home run.
Yeah, thank you. Yeah, I think that today's presentation, all presentations have good slides. So just I would like other people to follow the this kind of fashion. Yeah, also, yeah, overall, today's presentation, the data collection quality is very high. Yeah, so I was really impressed by that. Yeah, and on Thursday, and once again, make comments on each presentation in Canvas. You can see the quizzes, and your comment counts as 1 point as the quiz score. And unfortunately, I cannot really hold all presentations in Zoom, but the video presentations are also available. I have already made 1 presentation available, and probably I will publish 1 more presentation today. So watch the video and then make comments. And that's it. If you don't have any questions, let's see you on Thursday.